Two unbiased estimators are sitting in a bar. The first one says, "How do you like being married?" The second one says, "It's okay, but you lose a degree of freedom." Hopefully you get that. And actually, we're going to lose a degree of freedom when we start talking about confidence, confidence intervals and slopes. So when we calculate a regression line from a sample, it is called a sample regression line. It can also be called an estimated regression line, and it has the form y hat equals b naught plus b1x, where y hat is the estimated or predicted mean value for a given value of x. And then b naught is the y-intercept, and b1 is the slope. So whatever is the coefficient of your x, that's your slope. So let's go ahead and take a look at an example, and we want to determine the relationship between the mass suspended from a spring and the length of the stretch spring. We randomly selected masses ranging from 0 to 9 kilograms and measured the length of the stretch spring for each mass. Determine and interpret in context the slope and intercept for the estimated regression line. So here we're looking for the slope, and here I gave you an output, so a computer output. You're supposed to be able to read these as well. Now, I know that this column says coefficient, but we're looking for coefficient of the mass. The slope is always the coefficient of the units here, not the constant. That's your y-intercept. So that's what we're looking for. The way we interpret it is we say the estimate of the slope is 4.979. It is estimated that for every 1 kilogram increase in mass, the predicted spring length increases by 4.979 centimeters in length. Now, don't say the spring will increase. You need to have a little bit of a hedge there because these are just predictions on average. So now, if we're going to interpret the intercept, that is the coefficient of the constant, all right? Basically, your x to the not 0 power. And the estimate of the intercept is 63.679. It is that the average length of the spring is 63.679 centimeters when no mass is hung from it, all right? And notice the hedging there. We said the average. Don't say the length will be. So be careful with wording like that. Now we're going to go ahead and interpret the coefficient of determination, which is r squared. And on a mini tab output, it's going to be that number. And so we would say the coefficient of determination r squared is 99.32%. This value indicates that 99.32% of the variability in spring length can be explained by knowing the mass suspended from it. So that's your coefficient of determination. So now what changes on this lesson, that was a little bit of a review of what we just did. We're going to try to predict what is the possible true slope, or what is the possible true line for the length the spring extends compared to the masses, or basically for any regression you're trying to do. And the formula looks very similar, except we have mu y, which is the mean value, beta naught is the true population intercept, and beta 1 is the true population slope. All right. And we can infer the population slope from our sample regression line. So how do we do that? Well, first we need to make sure our conditions are met. And this is a nice acronym for remembering your conditions, LINER. L stands for linear. And basically that the relationship between x and y is linear. Check this by graphing the scatter plot of x and y, and I'll show you what I mean. If the pattern is roughly linear, that means there's no curving, then this condition is met. I stands for independent. Individual observations need to be independent of each other. Be careful with things over time, because time can change things. When sampling without replacement, make sure to check the 10% condition. That is, n is less than 0.10. And capital N, where little n is the sample size and capital N is the population size. N stands for normal, so the values of y are normally distributed for each given value of x. And we can almost never see this. If you look in your textbooks, what they're always going to show you is that you have this little normal distribution for every given value of x for the different y. So you're going to get some scatter around the line normally. But there is a way to check this. So what we do is we look at the residuals on a single histogram, box plot, or stem plot. And we'll say the condition is met if it does not show strong skew or outliers. Mild skew is okay. It's strong skew. And it's rare that you're normally going to have problems. It's not going to be a pretty normal distribution when you graph it. It's very rare because we don't have that many points. E stands for equal standard deviation. That is that the standard deviation of y is the same for all values of x. And to check this, you can graph the residuals versus the x values, and I'll show you that. If the spread looks roughly the same, no widening or narrowing for high and low values of x, then this condition is met. And finally, R stands for random. Data is from a random sample or a well-designed randomized experiment. So let's go ahead and check the conditions for our spring data. So here what I did is I just put in my data in list 1 and list 2 and did a scatter plot of list 1 and list 2, where list 1 is x and list 2 is y. That looks roughly, and by the way, when I look for my residuals, usually when I do a regression, if I have diagnostics on, it's going to create a list called residuals, and it's usually in 7. But this is going to be a scatter plot of x versus y, so list 1 versus list 2. Since this is roughly linear, the condition is met. Independence, the trials with the different masses were independent of each other, so we should be fine. There's no reason to think there was any dependence between one and the other. And then normality, the histogram does show a slight skew to the right, but it's not strong. And no outliers in the box plot or histogram. And it is normal to have minor issues in these graphs, okay? So as long as you don't have a giant skew or big outlier, you're fine. If we look for equal standard deviation, this is the plot. So I did a scatter plot where list 1 is the x value and the y value is that 7 resid list. And you can see that the spread's roughly the same across the different x's, so we're going to say that that condition is met. And then finally, random, it was given that the masses were randomly selected for the trials. Now we get to our main goal of this lesson, which is to create a confidence interval for the slope. What could the possible true values of the slope be? Well, we could attempt to capture the intercept, like I said before. Most of the time we're concerned with the slope. And it has the same form as what we have on our math chart. It's basically your statistic plus or minus your critical value times the standard deviation for the statistic. So in this case, B1, T star is the critical value right there. And we find that the same way that we did before with inverse T, except instead of having n minus 1 degrees of freedom, for lines we have n minus 2 degrees of freedom. And B1 is a slope from our sample regression line. That's a good estimate for our population slope. And S of B1 is the standard error for the slope. And on rare occasions, you can calculate it by hand using the formula on your statistics chart right there. Most of the time, you're not going to have to do that. A computer will normally give the standard error for the slope, and so will your calculator. And that is just the standard error for the residuals, and the denominator is the standard deviation of the x value. So the numerator is the standard error for the residuals. Denominator is standard deviation for the x values multiplied by n minus 1. We're not going to go into the derivation here. It's not required. So let's go ahead and construct and interpret a 90% confidence interval for our example with the spring. And we're going to use the Minitab output below. Now, you might be tempted to think that all of these values up here are actually down here. For example, you might say, oh, that's the t-value. Actually, that t-value is for a test and not for a confidence interval. So please ignore this value here. We're not going to use it. We're going to have to calculate our t-value by hand. And we're going to do that by doing t star is inverse t. How did I get 0.05? Well, I'm doing a 90% confidence interval. So if I do my graph, then I'm going to have 5% on each end. This will give me a negative value, but that's okay. And oh, here's my degrees of freedom, 14 minus 2. And I'm just going to use a positive value of that. Okay, so there's my t-value. It's not that one. See, those are incredibly different. Now, the other parts are in the output, which is basically your beta 1, or I'm sorry, your B1, and your standard error for the slope. So those two just go right in. 4.979 plus or minus 1.782 times your standard error here. and you end up with an interval of 4.767 to 5.191. So how do we interpret that? There's our interval, and we would say we are 90% confident that the interval from 4.767 to 5.191 captures the slope of the population regression line relating y equals spring length to x equals mass suspended on the spring used. So look at the wording. It's very similar to the wordings we were using before on confidence intervals. In this case, we're capturing the slope. Now, you can also do this on a calculator if you have a list of data. Don't expect to be able to calculate, to do an interval from a computer output using the calculator in the sense of just running a test. So here's how we do it when we have a list of data. On the springs, I actually do have the original list of data, so let's show you how to do that. So we're going to press Stat and scroll to Test. Then we're going to scroll down to G, line reg T int. And I bet you can guess we're going to use that F1 in the next lesson. So linear regression T interval is what that stands for. Your X list should be your list of independent values. Your Y list should be your dependent values. Frequency should be 1 in almost all situations. Confidence level, make sure you use the desired form of your confidence level, and then you scroll to calculate and press enter. Now your output, the second line shows the confidence interval for the slope. There it is right there. In fact, let me go ahead and highlight it. Highlighter. Right there is your confidence interval for the slope. And then the fourth line shows the degrees of freedom right there, which is n minus 2. So instead of 14, we have 12. The fifth line shows the standard error for the residuals. So don't mix this up with the standard error for the slope. So be careful with that one, okay? Then finally, if I were to compare the output here to what we got with the hand calculation, we got the same interval. The interpretation is the same. And again, you can only use a calculator to create a slope interval if you have a list of data. Most times you're going to have to calculate this by hand.